Test, test.
Okay, our next speaker is Paul Ryan. He's going to talk about separation of variables and how to use it to find structure constants.
All right.
Change, I suppose.
Yes. All right. Thank you. So let me start by thanking the organizers for the opportunity to come and present. It's always a great pleasure to be at IDD. So I'm going to speak about something that came out about 3 months ago with my collaborators, Till Bargier, Carlos Bertini, and Gabriel de Fundes. So I'm going to be quite broad and for the most part not technical at all. But let me try and set the stage by saying something that I guess most of you know, is that, does this work? Okay, it works. Planar n equals 4 super Young-Mills is an integrable four-dimensional conformal field theory. Okay, so why we like integrability is because integrability is very highly constraining. All right, it's very constraining for CFT data, scattering amplitudes, you can study Wilson loops, and so on. But so in the context of the spectral problem, one of the ways that integrability appears is the fact that the dilatation operator at one loop, as we just heard in the last talk, takes the form of an integrable spin chain. And this means that you can study the spectral problem of your theory by doing, say, beta ansatz methods. And this was eventually developed into the asymptotic beta ansatz for sufficiently large operators, which eventually developed into the thermodynamic beta ansatz for the complete solution of the spectral problem, for instance, by Gleb and Sergey. But the modern formulation of the spectral problem and its solution takes the form of something called quantum spectral curve. So many of you will probably heard the words quantum spectral curve, but maybe not super familiar with what it is. So let me just give, I guess, a very broad idea of what this thing is. So quantum spectral curve is a collection of functions. They're called Q functions. These functions depend on a complex variable u, which lives in some Riemann surface. So you have all of these Q functions, and they satisfy some relations. These relations are fixed by symmetry. And n equals 4 super Young-Mills. This is PSU 2,2/4. Okay? And you also have very special model-dependent analytic properties. So these functions have some branch points. The locations of these branch points are related to the Doof coupling of the theory. And then once you solve all of these functional relations with the required analytic properties, you can actually read off the conformal dimension of whatever state you're looking at. Okay? And some nice features from this is that you can really look at these conformal dimensions and interpolate from weakly coupled gauge theory all the way up to string theory. You can explore analyticity in spin and Regge trajectories. And quite recently, we did a systematic numerical strong coupling study by we're able to push the Doof coupling all the way to 150,000, which I think you would probably agree is quite strong coupling. Okay, so with quantum spectral curve, the spectral problem of n equals 4 super Young-Mills is effectively considered solved. Okay, in the sense that you take your favorite operator of the theory, whatever that may be, you plug it in to one of the nice Mathematica packages or C++ packages that we have, and it spits out the conformal dimension. Great. But this is a conformal field theory. Okay, it's not enough to just talk about conformal dimensions. We also need to ask, what about 3-point structure constants? Okay, so for 3-point structure constants, as Dennis gave a very nice overview of on Monday, there is the hexagon formalism. So the hexagon formalism involves taking your 3-point function as a pair of pans, cutting it into 2 hexagons, and then doing a couple of manipulations to these 2 hexagons. Okay? So I won't go into many precise details about this, but this formalism is very powerful. It's not just limited to 3-point functions. It has also been developed for higher point functions. And quite remarkably is that it's not even strictly related to integrability. You can also study non-planar corrections to correlators using this hexagon framework. But there are a couple of unsatisfactory features. So on one hand, in practice, this thing is limited to asymptotically large operators. Okay, finite size corrections are actually very difficult to incorporate in this framework. Next, features of CFT data that we know, like analyticity and spin, are not manifest in this framework. In this hexagon approach, spin is really a discrete integer number. Okay, so these beautiful Riemann surfaces that we expect from analyticity and spin are not manifest at all. Where are they hiding? So since we know that the spectral problem is solved with quantum spectral curve, and none of these problems are present there, we can do any operators, any length, and explore complex spin, no problem. What we would really like is, if the thing works, yes. What we would really like is some kind of quantum spectral curve based approach to correlation functions. Okay, so this would be fantastic because it would work for any operator of any size. It would work at strong coupling, and all of these things like analyticity and spin would be manifest. Okay, so schematically, what this would look like is we have our operators. To each operators, we have a collection of Q functions from quantum spectral curve. And what we would like is some functional, say f, which takes the Q functions of these three states and then spits out the corresponding 3-point structure constant. Okay? So this is a program which has been going on for a couple of years now, and quite a lot of people are involved with it. So to give you some indication that something like this is actually possible and not just a pipe dream, there's a very beautiful paper by Kolya Gromov, Andrea Cavaglia, and Fedor Levkovich-Mastyuk, where they look at the Cost-Wilson loop in n equals 4 super Young-Mills in so-called ladder's limit. So ladder's limit is a massive simplification where only a very select type of Feynman diagrams survive. And you can actually compute the expectation value of this Wilson loop exactly in terms of Q functions living at each cusp, living at each of the cusps. And the result takes this exact closed form at finite coupling in terms of these Q functions and involving these very simple integrals. So the lesson that you learn from this is to compute these types of objects, take Q functions, integrate them against some very simple measures. Okay? And when you stare at this long enough, what you realize is that the structure you get actually looks a lot like the expressions you would see in correlation functions in integrable spin chains when they are expressed in terms of Skleinen separated variables. And in this separation of variables framework, the whole point is that your wave function, say psi, factorizes into one particle wave functions, which are precisely these Q functions, which come from quantum spectral curve, Baxter TQ equation, QQ system, whatever you want to call it. Okay? So because of this, there has been a lot of research in this direction over the past couple of years. But when it comes to sort of the main goal, which is to really compute structure constants in planar n equals 4 super Young-Mills itself, there has not been a huge amount of progress. So the state of the art, really using this SOV formalism, is correlation functions of local operators in, say, the SU2 or SL2 sectors at low loops, up to 2 loops in this paper by these authors. And this is not really satisfactory because ultimately we really want to go beyond this. We want to really look at the full n equals 4 super Young-Mills. So what do we need to do? So we need more bosons. So we want to take SU2 and look at higher rank algebras. We want to take SU2 and start looking at SO6, for instance. SO6 is equivalent to SU4. We also need to add fermions because everything so far has been completely bosonic. And we also need to do more loops. So 2 loops is not very exciting. We want to look at all loops and fully non-perturbative structure constants. So for this talk, I'm going to talk. There's some delay. For this talk, I am going to tell you about how to add more scalars. So we're going to go beyond SU2 to a really higher rank sector. So SO6 or equivalently SU4. Okay, so let me just give you a sketch of the result without going into too many details. So to sketch the result, I need to tell you the precise setup. Okay, so planar n equals 4 super Young-Mills. Scalar sector, so 6 complex scalar fields, so z, z bar, x, x bar, y, y bar. I have a vacuum, which is, say, trace of z to the L. And on this vacuum, I start adding extra fields. So I add sprinkle some x's, some y's, z bars, whatever you want, okay? And in the integrability framework, this excited state is going to correspond to some excited spin chain state in my, say, SU4 spin chain, okay? So this is the setup we want. We have our one excited state in our 3-point function, and we want to width contract this to 2 protected vacuum operators. So this one will just be the complex conjugate of our initial vacuum, and this will be this sort of reservoir or rotated vacuum state. So this is a BPS operator, which is just rotated to be able to do the width contractions. It's not super important. But the point is that computing this 3-point structure constant means you need to compute 3-level width contractions. Computing 3-level width contractions is equivalent to computing a spin chain overlap by representing this excited state as a spin chain state and doing the width contractions or spin chain overlap with the other 2 states. Okay, so at most conferences or workshops, I would say this is the setup, but here I'm allowed to talk about twist without being heckled by the audience. Okay, so twist, what do we want to do with twist? So twist is going to break our global SU4 symmetry. We're going to break it down from SU4 to 3 copies of U1. And we'll do this by introducing 3 independent twist angles. So phi1, phi2, phi3. And these are going to live in our excited state, which now will also have some twisted trace. I'm not going to spell out the details super precisely. It's not super important. And then additionally, I'm also going to apply some additional global rotation to my BPS states, or my protected states, with some additional parameters omega and kappa. So I actually have 5 independent parameters now in my problem. I have these 2 rotation parameters omega and kappa, and I have these 3 twist angles phi1, phi2, phi3. So really what I'm ultimately going to compute is this object, which you can really view as being sort of a 3-point function in a deformation of planar n equals 4 super Young-Mills. Okay? Good. And this twist is actually very technically useful for separation of variables, which is actually the reason we do it in the first place. Okay? But it also, in the end, gets us access to some sort of really physical deformations like orbifold points and so on that Dennis told us about. Good. So let me just show you what the result takes like, what this combination of width contractions actually gives you in terms of the Q function from quantum spectral curve of this excited state. Good. So the result is some product of determinants. So I have this is my structure constant. This n is just some normalization. Doesn't matter. Doesn't depend on the state. Not important. Not interesting. I have this w, which depends on this omega, which was one of my global rotation parameters. I have this a, which depends on the other global rotation parameter, kappa, and I have this b. And each of these objects, they're some determinants of integrals built from my Q functions. So these brackets, this f bracket, is just a simple contour integral. So I have some measure with some poles at plus minus I/2. I just integrate around a circle. And these indices are not super important. I have some determinant. I have some determinant built from these integrals of Q functions. Then the claim is, compute these integrals of these Q functions. Evaluate this. Read off structure constant. Done. Okay, so this is a simple recipe for extracting the structure constants. Okay. Okay. Is there some optimal place to point at with the thing? I need to be closer. Okay, that does seem to be better, yeah. But it's more fun to stand over here. Anyway, okay, so I've given you this expression. Okay, I have, for the purpose of this talk, I have pulled it out of the air. Okay, you might say, okay, I have no idea where this comes from. Is there any qualitative check that I could actually do on this thing? That if you didn't know where this thing was coming from, because I haven't told you, what could you do to see if it reproduces maybe some physics that you might expect from the structure constant? Okay, so I will tell you how to do this. We can do one very strong consistency check on this result. So what is this consistency check? Well, it turns out that 3-point functions in n equals 4 super Young-Mills in the SU4 sector are very strongly constrained by what we would call quantum symmetries. So those of you familiar with Yangian symmetry, your mind may immediately jump here. So I do not mean Yangian symmetry, but it is something a bit like Yangian symmetry. It's some type of infinite dimensional symmetry which is present within the 3-point function. So what does this thing look like? So let's take a step back and let's view the 3-point function again. So strictly speaking, this is the original undeformed 3-point function, not the twisted one that I'm speaking about, but most of what I'm saying goes through. So we have this excited state and these 2 protected operators. So in integrability, excited state are parameterized by some beta roots. Okay? So in the SU4 sector, you have 3 flavors of beta roots. You have a U, which is so-called momentum carrying, and then you have 2 auxiliary families of roots. So this V and this W. And this V, U, and W are associated to the 3 nodes of the SU4 Dynkin diagram. Okay? So I have V, U, and W. Now, what is quite remarkable is this quantum symmetry statement that the structure constant vanishes completely, identically, unless the excited state is what we call left-right symmetric. So what does left-right symmetric mean? Left-right symmetric states are those where the beta roots in the 2 auxiliary wings are completely equal to each other. Okay? So a generic excited state will have 2 different families of auxiliary roots. Left-right symmetric states are those for which this Dynkin diagram is essentially invariant under flipping the two auxiliary wings. Okay? And the statement is that unless this thing is left-right symmetric, the structure constant is identically 0. Okay? So we presented this structure constant as some combination of Q functions. Is it possible that we can see this quantum symmetry manifestly at the level of this expression that I gave you? So it turns out we can, and I'll give a little motivation for how we can do that. So let's say a little bit more about this left-right symmetry and consider a sort of left-right symmetry transformation, which flips the two auxiliary wings of beta roots. So I want to take V, U, W and map to a new state which has W, U, and V. Okay? So in this SU4 spin chain, there are actually three families of conserved charges, which we label as, say, I+, I0, and I-, and there are a couple in each of these families. And the left-right transform, which maps me from this state to this state, at the level of integrals of motion, maps me from the plus family to the minus family. The 0 family is invariant, and the minus family goes to the plus family. Okay? So we have a symmetry transformation which implements this left-right transform. And so in earlier work with Simon Eckhammer and Kolya Gromov, we constructed a general framework for making such symmetry transformations manifest at the level of Q functions, which is ultimately based from looking at integral boundary states, which of course Charlotte has worked a lot on. And what we ended up finding from this general method we had, if you turn the crank, go through this sort of very constructive procedure, what you find is that you find a determinant of Q functions, which is 0 identically, unless this symmetry property is not satisfied. So when you go through this setup for this transformation, what you find is that this L by L determinant built from this Q12 vanishes identically if the state is not left-right symmetric. Okay? But this determinant of Q12 was precisely one of the building blocks that I had in my determinant, or in my structure constant. So if my state was not left-right symmetric, this W factor would actually be identically 0. And so from this, we can immediately read off that this infinite tower of quantum symmetries is actually satisfied or manifest from this expression. So this is a very strong consistency check. And actually knowing this symmetry property was one of the ways we actually derived this thing in the first place. Okay, so in the last 2 minutes, I guess, let me say something about the comparison to the hexagon framework, which is of course a much more well-established framework for computing structure constants. So again, in the hexagon frameworks, the beta roots are really sort of the key objects. Okay, so we have V, U, and W. And if you wanted to compute the structure constant using hexagons, you would need to compute these three objects. So this VW, which is a so-called wing Godin norm, it's like a Godin norm just built from auxiliary beta roots. You would have the Godin norm, which is the Godin built from the physical beta roots. And then you have this additional object here, this so-called hexagon amplitude, which means you need to split your correlation function over the two hexagons, sum over all processes where these excitations end up on two different wings. Okay? So we have these three building blocks, and it turns out, quite remarkably, that there is actually a one-to-one map between the hexagon building blocks and the separation of variables building blocks. So we have this structure, hexagons has this, and it turns out that after we remove the twist, because hexagons is really formulated for untwisted theories for the most part, that you end up with a precise one-to-one correspondence. That this W we had is precisely the wing Godin, this A is precisely the hexagon amplitude, and this B is precisely the Godin norm. Okay? And sort of one nice additional feature of this is that in a natural way, SOV provides a continuous deformation of hexagons. So we have not just hexagons, but we can compute the correlation functions for a wide range of deformations. Good. Okay, so let me summarize. So I've presented this expression for 3-point functions for you in terms of the Q functions of the corresponding state at tree level. Okay, so we need to solve the Q functions from, say, quantum spectral curve or TQ equations, and then we compute a couple of simple contour integrals. These integrals are trivial. Once you know the Q function, you plug in, you read off the 3-point structure constant. Okay, but what does this actually buy you? Okay, if I'm someone who really wants to compute structure constants in planar n equals 4 super Young-Mills, is this actually an advantageous method to doing that? And the answer is no, not really. But also, you would not use quantum spectral curve to solve an XU2 spin chain at one loop. So, but on the other hand, Q functions can be computed much faster than beta roots. So if you want to go to a very large number of roots, Q functions are actually much more advantageous. And these expressions we have should eventually allow us to analytically continue structure constant in spin, which probably has some energy correlator applications. And we also know that Q functions are the natural objects at finite coupling. Okay, so we're also looking at conformal fishnet theory right now, where we are able to really put this into practice. We can compute finite coupling structure constants from quantum spectral curve and separation of variables. And we also know that what we see here is that this SOV and Q function approach seems to work when hexagons fails. And we can also use it to match the orbifold computation of Dennis and Torben. Okay, so let me just mention some brief outlook. Well, one is alluding to something I mentioned at the beginning, that we know separation of variables expressions for correlators up to 2 loops. But the results are not particularly enlightening. They're honestly a bit of a mess. And so using the methods that we developed in this paper, which I would encourage you to read if you make it all the way to Appendix Q, revisiting this would be sort of useful. There's also a sort of unrelated approach to SL2 sector correlators at all loops from work by Benjamin Basso, Alessandro Gorgadis, and Arthur Suero, where they also compute structure constants using quantum spectral curve objects. Eventually, of course, we want to extend to PSU 2,2/4, and supersymmetric SOV is still a major open problem. Next, of course, we want to really put all of that into practice in fishnet, which is something we're currently doing. And eventually, and maybe more schematically, structure constants for your favorite deformation of n equals 4 super Young-Mills, whatever that may be. The methods should more or less apply. So I guess with that, I will thank you for your attention.
Thank you, Paul. Questions?
Paul, thanks for the very nice talk. So you said that the method works when the hexagon fails. Can I interpret this as like the method provides a way to how to modify the hexagon? Like if you still want to use like something like the hexagon, does your method give a prescription what would have to change in the method? Is that the right interpretation?
It's certainly a possible interpretation, and also one which works in practice. So I mentioned this thing here. Is this it? No. Next one. Yeah, this. So I said that we have a precise match between hexagons and SOV for the untwisted theory. This is okay. This is not completely the general story. We actually match precisely with hexagons for a more general class. So when we put this omega to 1, we also match hexagons, provided you twist this sum over hexagon amplitudes in a simple way. So you would need to essentially put some factor of kappa in the sum over partitions, and then you also match that. We don't immediately know how to implement this omega deformation that we have here into hexagons. Probably you need to do some additional global rotation there, do some additional twist. But in principle, yes, it does provide a prescription on how to modify hexagons if you really set up like a one-to-one map. Yeah.
Thank you.
Thanks. So all of this, of course, reminds me a lot about integral boundaries. So we want to imagine some argument based on Italian group theory to tell you what correlates to.
Right. Okay. So you want sort of a general framework which would tell me, like, based on, say, the geometry of my correlator or something like that? Yeah, so that's a great question. I do not immediately know the answer. So for instance, when we were developing all of this, we sort of used the fact that we knew that the structure constant had this infinite tower of these quantum symmetries. But it's not at all clear just from looking at the correlator why you would expect to have these. It certainly does not follow from any classical statements. It's not a statement about, say, global quantum numbers, SU4 quantum numbers. Yeah.
The same for APJM?
Yes, so we have been trying to do APGM. Some of it. Right, so the representation is different. So here we're in the antisymmetric representation. In APJM, we have alternating fundamental, anti-fundamental. we tried some very sort of low-level experiments, which say just an excited state built out of length 2 and contracted it to 2 protected operators, and there it worked. Then we got distracted with some other things and couldn't really say anything concrete and never revisited this. But from the initial experiments we did, yes, the methods did apply to ABGM.
First comment also, so what you find is that your roots at outer two nodes have paired,
Yes.
but for the one-point function have to be paired. At single.
Yes.
ABGM is the opposite for the one-point functions. So maybe it would also be the opposite for you.
Okay, that would actually be fantastic because this is one of the things which went wrong with ABGM, was that we did not have the precise pairing we expected. Okay, we should probably discuss that a bit more then. Yeah.
Thanks. So my question is related to this left-right symmetry that you were mentioning earlier. So I guess the statement is something when you only have one excited operator and the rest are vacuum.
Yes.
Okay. Because in general, I could imagine that I put like SU3 states and like 2 or more positions, and then I just excite the left or the right wing of the diagram for these states. Did you also look into structure constants for these things, or is it really just for one excited operator at the moment?
For what we did, it was just one excited operator. Yeah. But I'm told this left-right symmetry persists generally.
But probably for the whole 3-point function, not for individual operators, right?
What do you mean for individual operators?
I mean, like if I consider one operator in SQ3 sector where I just excite the left wing, and then another operator where I just excite the right wing. Then I guess, and the third is a vacuum, of course. And I guess it's just a statement about overall charge conservation.
Yeah, so that's a great question. I don't know the answer because actually in the paper, like this paper by these authors that I mentioned, they have a very mysterious comment where they say left-right symmetry persists for more excited states. They do not say under what kind of context this actually happens.
Okay, because we have 3-point function, I mean, some structure constants for like 2 excited operators in that but maybe we should. Thanks.
So if I understand correct, you only need Q functions to find structure constants.
Yes.
Does it mean that as soon as you know the spectrum of a CFT, you know the structure constants of the CFT?
I definitely do not want to make a blanket claim on CFTs in general. For n equals 4 super Young Mills, based on experiments which have been done and what we see here, it does seem to be indicating that spectral data completely fixes the theory. And so I used to have a comment at the end of this slide that it's clear that quantum spectral curve gives you far more than just the spectrum. Of course, we see here structure constants, but in some simple examples, we also see maybe perturbatively and at least at tree level that you can actually use quantum spectral curve to reconstruct, say, the quantum algebra, which is governing this thing. So for example, rebuild the Yangian directly from quantum spectral curve. If that is something which persists, say, at finite coupling, then the answer would be yes. Because of course, if you have a quantum algebra, then you know everything. So I don't want to make a universal claim, but
Okay, thank you. Okay, let's thank Paul again.